Hello everybody, this is video 16.3, which is on calculating the probabilities of compound events. Again, as usual, make sure that you've looked at sections 16.1 and 16.2 before starting this section. We're going to be using a lot of the ideas from the previous sections to start to look at how we can calculate some probabilities of some more complicated events. This will lead us to section 16.4, where we'll use fractions to do some of the calculations. So this is sort of a basic introduction to calculation, and then the next video in 16.4 will give us a little bit more in-depth look at a more abstracted process for calculation. But here we go. So we've got two terms here, independent and dependent. These are not new terms. These came up in the previous set of slides, but we're going to be talking about this idea a little bit more in this section. So I want to take a moment to sort of review these two terms. So independent, if we remember, means that the outcome does not depend on previous outcomes. And we talked about this in terms of the jar with marbles in it. If I pull the marble out and I look at it and I put the marble back in, the probabilities don't change. The number of total marbles has stayed constant. The number of marbles of that color that I drew stays constant. Everything stays the same. So if I keep drawing marbles out and putting them back in the jar, if I do that 100, 200 times, nothing has changed. Now, we compared that to dependent, where the outcome does depend on previous outcomes. And we talked about that jar having 10 red marbles and 30 marbles total. And if I pull that first marble out and it's red, and I don't put it back in the jar, well, now the total number of marbles has changed, and the total number of red marbles has changed. So the probability of drawing a red has gone from 10 out of 30 to 9 out of 29. This is what we mean by dependent. That each of the outcomes is dependent on what's happened before. So one of the things I wanted to bring this up to talk about is that it's not the physical construct of the problem that really dictates if it's dependent or independent. If I have those marbles in that jar, that's neither inherently dependent or independent. It's what I do with the marbles, specifically if I replace them back or not, that makes it a dependent or independent trial. So before answering a question about whether or not something is dependent or independent, make sure you look at what's happening in the experiment and really ask yourself, after repeated trials, after repeated outcomes, is the probability changing? And if you can see a case where it is changing, then it's probably dependent. If you see that it's not changing over any number of trials, then it's probably independent. So we have a tree diagram here where we have three coin tosses. And so we're flipping a fair coin. We have two outcomes, the two sides of the coin. We've got heads or tails. And so we've got our first coin toss here, our second coin toss here, and our third coin toss here. And we've looked at tree diagrams before, but just as a little bit of review, on this first coin toss, I'm either going to get heads or I'm going to get tails. Now, if I flip heads here, I again can get heads or tails on the second coin toss. So again, just a reminder that the second coin toss doesn't have four outcomes. There's still only two outcomes, even though there's four things in this column. There's these two outcomes that go with this outcome, and then there's these two that go with these. So now this third coin toss, we still have only two possible outcomes. We've got these two that go with the heads. We have these two that go with heads, tails. We have these two that go with tails and then heads. And then we have these two that go with tails, tails. So even though it looks like we've got more than two outcomes, the structure and nature of the tree diagram makes it look like we have more than two outcomes, but we still only have two outcomes. The coin hasn't mysteriously gotten more sides to it. There's still only two sides to the coin. If we look over here, we can see the outcomes. And so we have these in parentheses here because remember, these are These would not be ordered pairs because we have more than two things. These would be ordered triples. Um, so these would be ordered triples because we have three things here. Uh, so remember that this is in order. So that's the first part of this. So we've got the first coin toss result, the second coin toss result, and the third coin toss result. So if we look at this outcome, HHT, if we start here at the beginning of the tree diagram, we can see that that is specifically heads first, heads second, tails third. That gives us heads, heads, tails. Now that's different than tails, heads, heads. Even though they both have one tails and two heads, but remember this order tells me specifically that this would be, and I'll switch colors here to red, that this would be tails and then heads for this one. I'll erase that black line. We'll go back to red, and that's here. So even though these look like the same thing, they're both two heads and one tail, the ordered part of this is really important because it lets us know the sequence of events that took place to get to that outcome. This is important because in a problem like the first one, the probability of heads, 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 there's only one way to get this, and there's 8 total outcomes. So we know the probability here is that it will happen one time out of 8. There's one way that this can be satisfied, and then the size of the sample space, the number of possible outcomes is 8. So I have 1 out of 8. We can see one outcome here out of the possible 8. Now, if we look at these two problems, what is the probability of tails, heads, heads? Well, this can only happen one way again out of 8. But if we look at what is the probability of getting heads twice, that's a different question. And it seems like the same question if we don't remember and don't keep in mind that these parentheses mean that order is important. So if we look at how many ways can I get heads twice, we'll erase all these lines here. So how many ways can I get heads twice? And I'll do this in blue to kind of keep things separated out. So here I get heads twice, here I get heads twice, here I get heads twice. So there's 3 ways of doing it out of 8. So again, the difference between these two questions is how much we remember and understand about ordering being important. This tails, heads, heads is only one case. This getting heads twice is 3 different cases. So it's a very subtle difference in the language, but it's a very big and important difference in the mathematics. Real quick, I want to talk about the difference between flipping 3 coins one time and flipping 1 coin 3 times. You'll notice in your book that when they flip 3 coins, that the 3 coins are all different coins, that it's like a penny and a quarter and a nickel. The reason is so we can see how the 3 outcomes are different. If we flipped 3 pennies, then it's going to be really hard to tell the difference between tails, heads, heads, tails, heads, heads, this one, and heads, heads, tails. They're all 3 pennies. So if we flip 3 different coins, then we can make this the penny result, this the quarter result, and this the nickel result. If talking about things in this ordered way of the same coin is going to be too complicated for your students, or maybe even for you, making the 2 coins or making the 3 coins or however many coins different coins makes that order more explicit and makes it more natural. In the same way, you'll see a lot of problems dealing with probability where there's 2 or more dice. There'll be different colors. You'll have a white die and a red die, or a white die, a red die, and a black die, and they'll all be different. And again, the same reason is because now we can talk about the white result, the red result, the black result, and then the order is implicit in that. So it's not because we lost a dice and we had to go, or lost a die and we had to go take one out of a different game and replace it. It's so we can see the order of what's going on. Now, I want to look at this spinner that's got 5 outcomes, and we want to find the probability that we get a 1 on both spins. So we're going to go through this problem twice, and I'm going to go through it one time showing a really common mistake that we could make with this problem, and that we need to really watch to see that students don't make this mistake, or that if they do, we're ready to explain to them why that doesn't work. So I've got my spinner here. I've got three outcomes. I can get a 1, a 2, or a 3. So I'm going to draw my tree diagram. Here's a 1, here's a 2, and here's a 3. And then from this, on my second spin, I've got three outcomes. 1, 2, 3, and then also three outcomes. 1, 2, 3. So the probability to get a 1 on both spins, there's one way for that to occur. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 out of 9. This seems like a natural answer. And I'm going to guess and hope most of you recognize this does not work. This is no good. The reason this doesn't work is because this assumes that all of these have equal probability. This approach assumes that everything has the same likelihood of occurring. In the previous problem, we were doing coin flips, and we were assuming the coins were fair, and they each had a 1/2 chance of coming up heads or coming up tails. Here, if we look at the spinner, we can tell the probability of a 1 is 1/5, the probability of a 3 is 1/5, but the probability of a 2 is 3/5. So we do not have, using the language earlier in the chapter, a uniform probability model or a uniform probability distribution. We don't have the same probabilities going across this problem. If this spinner was broken into 3 sections like this, and they were numbered 1, 2, and 3, then this would work. This would absolutely work, because we would have 3 regions, all of the same area, so now we have a uniform probability. But given this spinner right here, that's not going to work. So we want to make sure that students are not just looking at the possible outcomes, but the likelihood and the probability of those outcomes. We'll look at in 16.4 a way to use fractions to sort of do this calculation in a much easier way. But for right now, we're going to look at doing it in a more concrete way that will allow us to see what the actual probability would be. So method 1 of solving that spinner problem that we just looked at is to use what we're going to call a uniform probability model, UPM. So this is my uniform probability model tree diagram. What that means is I'm going to draw the tree diagram, but I'm going to draw it in a way that shows all the possible outcomes with uniform probability. So what I mean by that is this. I'm going to draw my tree diagram going down instead of going across this time. So I'm going to write out all the possible outcomes. So now you can see that we've written out 5 outcomes, and each of these has a probability of 1/5. 1/5, 1/5, 1/5, 1/5, 1/5. Now, if I wanted to look at what's the probability of getting a 2, then I would add up the 1/5 here, the 1/5 here, and the 1/5 here to get 3/5, just like we saw in the previous slide. But for right now, for the purposes of this problem, we're going to leave things as they are. Now here, I'll do the same thing. So on my second spin, I've got 5 outcomes, 1, 2, 2, 2, 3. The same thing here, the same thing here, here, and here. 1, 2, 2, 2, 3. And so by writing everything out, now I can see how many actual outcomes there are. I can see that there's 5 plus 5 plus 5 plus 5 plus 5. So my actual probability of getting a 1 and a 1 is going to be out of 25. And then how many ways do I have a 1 on both spins, just one. So the number of ways of it occurring hasn't changed. There's still only one way for it to happen, but the total number of possibilities should be 25 instead of 9. Now, as you can imagine, this is going to be a really cumbersome way of doing these problems, especially as the number of possibilities gets bigger and bigger and bigger. If the spinner had, say, 8 sections instead of 5, this is going to be a really big tree diagram to have to draw. So like I said, in section 16.4, we'll look at doing this in a more abstracted way using fractions. But for right now, we can use this concrete way, especially for much smaller problems, to show that if the probabilities of the outcomes is not uniform, there's a way to draw the tree diagram in a way that makes it uniform to see what's going on in the problem. The last topic that we need to talk about is kind of an optional topic. You may not see it very much, but I do want to go through this very quickly just to introduce it, and it's the idea of expected value. Expected value, the book calls the average outcome of the experiment in the ideal over the long term. That in the ideal is maybe a little confusing, and really what that means is that our probability model, the assumptions that we're making, we're doing this enough times that everything gets worked out. So any sort of like luck or variations that might experience in the problem all sort of get worked out. As an example, if I'm flipping a coin, the probability of getting heads 2 times in a row is 25% of the time. I mean, it's not an unlikely thing, but getting heads, say, 100 times in a row or 1,000 times in a row, that becomes really unlikely. So it's really in the ideal and over the long term are kind of the same thing. What this is telling us is we're going to do this enough times that everything gets worked out and that we start to get things, we're starting to get the theoretical probability. We're getting more and more likely what we're supposed to be getting. So to talk about this, I want to look at 2 games real quick. And I'll warn you, like examples like this, you'll have to gauge how appropriate it is with your students. You may want to change it to where you're flipping a coin and you're losing a bottle cap or a matchstick or something. I'm using dollars here, but you know, if you're concerned that it'll seem as though you're talking about gambling and that sort of works against the um, what am I trying to say here? If it works against the environment or community that you're in, you certainly change it to something else. Anyway, so we're going to flip a coin. If it comes up heads, you win $1. If it comes up tails, you lose $2. Is this a fair game? A lot of students will say that this is a fair game. Why? Because you have half a chance of winning and half a chance of losing. The probability that you win and the probability you lose are equal. And that's true. But as you probably notice, when I win a little bit, and if I lose more than a little bit. I lose twice as much as I stand to win. So you can probably tell right away as an adult that this is not a fair game. Expected value allows us to quantify exactly how unfair it is. So what I have here is the probability that I win, and then the outcome. How much do I stand to win? So this is my win amount. This is my probability that I lose. And then this is how much I stand to lose, in this case, minus $2. Now, this plus doesn't really need to be there. It's really this positive 1. I could just write it as a 1, but I wanted to put the plus sign in there to really reinforce that this is a win, that you know we're increasing by the dollar. But some of you may recognize that it's absolutely not necessary to be there. So I've got minus a half, or I'm sorry, I got plus a half, minus 2 halves, and that gives me negative 1 half. Now, what this tells me is every time I play, I expect to lose 50 cents. Is it possible to play one time and lose 50 cents? No, and this is where the over the long term is important. So while this isn't really possible to happen, if I play 100 times, then I expect to lose $50. and that could happen. That certainly could. That is an outcome that is possible. So as we increase the number of games, then this starts to become ideal, quote unquote. We start to get a result that actually makes some degree of sense. Um, so it doesn't really work empirically over one trial, but it absolutely begins to work the more games that we play. The second game here, we're rolling a fair six-sided die, and if it comes up a six, we win $11. And if it comes up anything else, we lose $1. Now, this is sort of the opposite of the first game because we only have a 1 in 6 chance of winning. It seems really unlikely that we're going to win. So again, a student might think that this is not a fair game because you don't have a very good chance of winning. But expected value shows us that when we do win, we win $11, and when we lose, we only lose $1. So every time we play this game, we actually expect to win $1 each time we play. So even though the probability is against us, the outcome more than offsets our slim probability of winning. We win enough on each game that it actually makes it unfair in our favor. This is actually would be a good game for us. This may not be a topic that you have to do with your students. This is certainly a much older topic. So if you're going to be doing kindergarten 1, 2, you may not see expected value, and you may not see it until grades 5 or 6. But it's a good topic to show students so they start to understand how we can quantify fairness. And I'm not going to lie, it's a good topic for adults to sort of be reminded of as well. So our checkpoint problem, I want you to go back and look at that spinner with the 1, 2, 2, 2, 3. So can you find the probability that on 2 spins, the sum of the 2 numbers that come up is even? We already kind of drew, well, we drew the wrong tree diagram. Don't use that one. But we drew the right tree diagram. So look at that tree diagram or think about what you understand about probabilities and see if you can find the probability that the sum of the 2 spins is even. Section 16.4, we'll look at this a little bit more, and again, like I said, we'll look at a more abstract way of calculating these probabilities. But you have a tool now to be able to answer this question. Speaking of questions, if you have any questions, by all means, please bring them to class. We'll get them answered. Thanks.